Okay, why is this not working? Ta-da! Okay, it works now. All right. So, rotation on a fixed axis. Now, so far, whatever we have done has always been moving in a straight line. The only time we look at circles is when we did circular motion. And even then, it was an object going in a line that looks like a circle. But it was not rotating like this Ferris wheel is in the photo, or like this letter R is doing. It was not rotating by in itself. So chapter 10 is all about this rotation bit. Okay. So the first thing first, just like we did for translational variables, we'll look at rotational variables. How do we define the problem? How do we describe what is going on? And what we do is we will end up doing some form of translation where we translate from one language to another, where we translate from the language of translational variables to rotational variables. Okay, some people are seeing the screen, some are not. If you are unable to see the screen, try logging out and back in again. Sorry, I tried changing the link. So this is a different link this time. Yeah. Okay. Actually, there might be one thing that we might be able to do to help. Is anyone else's? No, no one's camera is on. No idea what's going on. Sorry. Okay. So what we do is, whenever something is rotating, there is at least one place where it is fixed. And we call that محور الدوران, rotation axis. Okay. So if you take an egg like the one in the photo, you have to make it rotate, you have to fix it in some place and rotate about that axis. So we call it a rotation axis. Now, if I want to look if something goes from point A to point B, I usually define a point on that body and I see how much does it move. Now, I do the same thing for rotating bodies. I define this, which I call a reference line. It's any point. I choose some place and I draw a line through it perpendicular to the rotation axis. And I say, okay, this is my reference line. Any measurements I do will depend on this. Okay. Now, let's take a look at something that is moving. Yeah. Now, if I take this my purple reference line and I want to move, this thing is going in a circle. I look at it. The same thing happens when I look at a fan and I look at just one of the blades. It will end up going in a circle, right? Okay. Now, in linear motion, when I want to move from one place to next, I call it position x1, position x2. Here, I describe it from my initial position as θ1 and θ2 in angles. Okay. Now, when we look at linear position, we don't have an issue. Yeah. This is the point of x1, this is x2, this is x3. Defining this distance is not difficult. Delta x plus delta y, it's not an issue. But when we come to rotation, there is something weird going on. Say, initially, I am here, okay? And I want to go all the way here. So I moved my line. Where do I measure my distance, how much I moved? Is this a good area to measure it? Here, I moved the distance s. Or perhaps this is a better area. Or maybe if I go really nearby, it's better because it's closer to the rotation axis. Now, taking this distance is problematic because each one of them, as you can see, changes in length. So if I'm trying to say it moved from point A to point B, how can I describe it if every time I try to measure it at a different place, it gives me a different result? This doesn't work. What's a better way to measure the movement? One that does not change depending on where we measure it from.
The angle.
The angle is an excellent option. The angle actually relates this changing s to how far away are you from the rotation axis, the radius or r. Okay, so it gives you a fixed number no matter where you are. Okay, now Mariam, you mentioned define a point on the shape at the end. The only problem is, okay, that it will give us different results with different shapes. So it's not a it might work for one shape, but then you will need to have 10 different rules for 10 different shapes. And that's not very elegant. It's also a headache. Okay, so if this guy goes one revolution, دويرة واحدة, how many degrees does he go through?
360.
Okay. And what's the distance he has gone through?
2 pi.
2 pi r. Now, if I say he has gone 2 pi r, and I want to find theta, so it's s over r. 2 pi r over r, I end up with 2 pi radians. So one revolution, 360 degrees, 2 pi radians are exactly the same thing. 1 radian is about 57.3 degrees. Okay. Now, if I want to, since we have decided that theta is a good unit or a good measurement to define changes, if I am going from place A to place B, I should do delta theta equals theta 2 minus theta 1. Just like with linear variables, we did delta x equals x2 minus x1. Now with linear variables, we don't have an issue. We go this way, it's positive. We go this way, it's negative. But for angular displacement, how do we define positive and negative? There's a convention, okay, it's called the right-hand rule, in that clockwise is negative and counterclockwise is positive. Now, I got very confused by this when I was a student, so I decided to make up my own way to remember which one is positive, which one is negative. If I am going clockwise, time is passing, I am getting older, and I don't like being older. Okay, so that's a negative thing, not cool. On the other hand, if I'm going counterclockwise, it's like I'm going back in time. And hey, that's really, really cool. I would do anything to be able to go back in time. So that's positive. That's a good thing. Now, knowing what we know so far, if I want to define angular velocity, how would I define it? For linear variables, velocity was delta x equals x2 minus x1 over time. For rotational, we translate it to the rate of change of distance, which is θ2 minus θ1 over t2 minus t1. So delta theta over delta t. And we give it the symbol omega. Now, to differentiate between translational and rotational variables, we use different alphabets. For translational variables, we use the Latin alphabet, A, B, C, D, E, F, G. For the rotational variables, we use the Greek alphabet, which is alpha, beta, gamma, delta, and so on and so forth. Okay, so x becomes theta, v becomes omega, and since the average angular velocity is delta theta over t, delta t, in radians per seconds or revolutions per seconds, what would the instantaneous angular velocity be? The instantaneous would be d theta by dt, just like v was dx by dt. Okay. Now, let's do a PIQ. If you go to Moodle, the results of quiz 4 will be announced, will be online right after this lecture, by the way. I've received quite a few emails asking about it, so it's going to be right after this lecture. Okay. So the question is, the diameter of the sun is 400 times greater than that of the moon. By coincidence, the sun is also about 400 times further away from the Earth than the moon is. For an observer on Earth, compare the angle subtended by the sun, theta sun, and the angle subtended by the moon, theta moon, as shown in the figure below. Are the angles of the sun much larger or the moon much larger, or are they pretty much equal? Let's take a look. So 57, only about 20 people have responded so far. And the answers are pretty equal. I'll give you about 20 more seconds. Okay. Let's see. Almost twice as many people chose option C as option A. The angles subtended by the sun and the moon are approximately equal. Okay, that's fair enough. Let's see. The sun, we said, has a diameter of 400. The moon has a diameter as a distance d and a diameter s. The sun has a distance 400d and a diameter of 400s. When we look at theta, we said it's s over r. So for the moon, it will be d over r, and for the sun, it will be 400d over 400r, which is still d over r. So actually, if we superimpose them, they actually give us perfectly the same angle, which is why having total eclipse is even possible. Otherwise, it wouldn't. Okay. Knowing what we know, what is our angular acceleration? Our angular acceleration will be delta omega over delta t, and it will be given by alpha instead of a. The instantaneous angular acceleration will be given by d omega by dt. Just like for linear variables, it's given by a equals dv by dt. For linear variables, we have meters per second square. Here we have radians per second square. A child's top is spun with angular acceleration alpha equals 5t cubed minus 4t, with t in seconds and alpha in radians per second squared. At t equals 0, the top has angular velocity 5 radians per second, and the reference line on it is at an angular position theta equals 2 radians. We want an expression for the angular velocity omega of t of the top. That is, the question says, find an expression that explicitly indicates how the angular velocity depends on time. Well, if the question gives us that alpha is 5t cubed minus 4t, then omega is one step back, so we integrate, and we end up with 5t4 by 4 and minus 4t squared over 2 plus a constant. Now, we don't leave it at plus a constant because we already know that at t equals 0, it has an angular velocity of 5 radians per second. So at t equals 0, c is equal to 5 radians. So our actual formulae would be 5t to the power 4 over 4 minus 2t squared plus 5. Now we want angular position. Again, we already have velocity because we integrated acceleration once. We integrate it again, and we end up with we end up with 5t to the 5 over 20 minus 2t cubed over 3 plus 5t plus c. And then we need to find c. Now a question is, all of our quantities when linear are vectors. So when they're angular, are they still vectors? Yes, some of them. What we do is we use the right-hand rule to establish the direction of the angular velocity vector. I curl my fingers around the direction of the movement, and where my thumb points is the direction of my vector. So if my CD is moving clockwise, then my thumb would be down. So it's a negative velocity, angular velocity. If it's going counterclockwise, then my thumb would be pointing up and it would be positive. Omega and alpha both follow vector addition. If we have an omega and an alpha, we want to add them, we want to subtract them, they do follow vector addition. But I did not say anything about displacement. Angular displacement is actually a little bit weird. I want each and every one of you, I'll give you a minute, to go get a notebook or a textbook. It doesn't matter what book, just get me a book, something rectangular. Go, I'll give you a minute. Okay, I'll assume that everyone got one. Let's do something. Let's take a book and first rotate it 90 degrees along the x-axis. It will look like this. Then rotate it 90 degrees along the y-axis. It will look like this. Yeah? So far, so good? Now, I will return the book like it was. But now, instead of rotating x then y, I will rotate y then x. عادي. 2 زائد 3 5 و3 زائد 2 5 صح؟ ما عندنا إشكالية. So rotate along the y-axis, then rotate along the x-axis, and we have a problem. Rotating x then y gives me a different result than rotating y then x. So when we come to angular displacements, actually 2 plus 3 and 3 plus 2 are not the same thing. So angular displacement is not a vector. Okay. It's a different thing. It's treated differently. Angular displacements are not vectors. Because a key property of vectors is that they're commutative. Yeah. A plus B equals B plus A. Now here, obviously, x plus y is not equal to y plus x. So it's not a vector. It's something else. Did you all try it? Did you get the same result? Did I make a mistake?
Yes.
Okay. Now, let's write stuff down. These are our quantities for linear motion. X minus x naught, so delta x, or as I used to call it S. V for velocity, T for time, A for acceleration, V naught, or I used to call it U. For rotational motion, translation, theta minus theta naught, you can still call it S if you want to. Actually, no, call it delta theta. Omega instead of V, T is still T, alpha instead of A, and omega naught instead of V naught or U. Different, but the same. I'll give you a minute, write this down on a piece of paper because we're going to be using it extensively in the upcoming slides. Okay. Let's do some translation. For linear motion, we had V equals U plus AT or V naught plus AT. Translated to rotational motion, what do we get? Omega equals omega naught plus alpha T. Same equation, just different letters. They even look the same. S equals UT plus half AT squared. As theta equals omega naught T plus half alpha T squared. V squared equals V naught squared plus 2A delta X. Omega squared equals omega naught squared plus 2 alpha delta theta. Delta X equals half the average of the velocity. Same thing, but for angles. And so on and so forth. Whatever equation we have for linear motion, we can use it for rotational just by changing the variables. Okay, but the whole equation needs to be changed. So you cannot use omega naught with A. If you use omega naught, it has to be alpha. If we use A, you have to use V naught, and so on and so forth. You cannot mix and match. Example, the angular velocity of the cylinder decreases from 3.4 radians per second to 2 radians per second in 20 revolutions at constant angular acceleration. What is this constant angular acceleration? Well, our change in theta is 20 revolutions. That is 125.7 radians. We said that each revolution is 2 pi radians. Omega naught, 3.4 radians per second. Omega final, 2 radians per second. We use our lovely equation, V equals U plus AT. Otherwise, now for rotation, omega equals omega naught plus alpha T. And we also use delta theta equals omega naught T plus half AT squared. And we get our answer. No complications. Now, how do I relate the linear and angular variables? A good question is, طيب دكتور أنت قلت لنا إنه we cannot mix between linear and angular variables. If I use V لازم A وإذا استخدم omega لازم alpha. طيب افترض أنا عندي سؤال أو عندي مشكلة أو عندي مسألة. I have some but not all of the variables in different formats. Say for example, I have A and omega naught. I cannot use them in the same equation because you said it has to be consistent. But I do have this information, so what do I do with it? Well, we need to translate. Either we make the A become alpha or the omega becomes V to be able to speak in the same language. Okay, so either you're speaking English or you're speaking Arabic. Now, this might be a bad example because apparently we are used to, mixing and matching our two languages. كيف حالك؟ تعال quickly بيتأخر علينا lecture. We're used to this in Arabic. But believe it or not, other languages do not accept this. Okay? If you speak to a French person and he goes, Bonjour, comment ça va? You'll be like, what? No, you mixed up two different things. Try that again. Okay. If you speak to a Spanish person and he goes, Estoy bien, and you go, Ana zin, you're like, huh? Use one language, mate. This doesn't work this way. I'm speaking to you in Espanol, you speak to me in Espanol. Or if I know Arabic, then we speak Arabic. We cannot mix and match. So, translation. Here's some weird looking shape with a pipe in the middle of it to be its fixed rotation axis, and it's rotating. Now, I have two people on this same rotating object. And things are about to become very spooky and very weird. Let them go a full circle. Okay. Now I have two of these people. الأحمر هي العين الحمراء هنا والأزرق هو اللي العين الزرقاء هنا. Now when they go a full circle, they both go through how many degrees? 360 degrees, صح? But if we look at the circumference, at the linear distance each one of them moved, they have moved very different distances. While both of them have gone 360 degrees movement, the red guy has obviously moved way more distance than the blue guy. And things start becoming very weird here very quickly. Not only have they moved in a different distance, did they do it in different times or the same time? Same time. So if they move two different distances in the same time, what does that tell us?
Different velocities.
Yeah, we have different velocities, but different, same angular velocity. This is what happens. If I trace them, this is what I see. Just take a look. It looks like the blue guy is moving at a different velocity than the red guy. So we do some translations. Okay. Position, we have already said theta equals S over R. So my distance moved as S equals theta times R. Speed, V equals omega R. Acceleration, A tangential, because we're not looking at the radial component now, A tangential equals alpha R. So if we want to go from the angular variable to the linear variable, we simply multiply it by the distance R from the rotation axis. So far, so clear? Any questions so far? Okay. Now we have two types of acceleration, linearly speaking. Whenever we were talking about circular motion, we had tangential acceleration, which is the straight line, but we also had centripetal acceleration, right? Radial acceleration, which we had already said, defined before in chapter 5 or chapter 6 as v squared over r. Now, since we have already determined that v equals r omega, that means r squared omega squared over r. So it's omega squared r. Okay. So if we want the tangential acceleration, we multiplied alpha by r. If you want the radial acceleration, we multiply the velocity squared by r. Let's do a sample problem. We are given the job of designing a large horizontal ring that will rotate around a vertical axis and that will have a radius of 33.1 meters. Passengers will enter through a door in the outer wall of the ring and then stand next to that wall. We decide for the time interval t0 to 2.3, the angular position of a reference frame of the ring will be given by theta equals ct cube, with c equals 6.39 times 10 to the minus 2 radians per second cubed. After 2.3 seconds, the angular speed will be held constant until the end of the ride. So this is what we usually do في الألعاب في الملاهي. Once the ring begins to rotate, the floor of the ring will drop away from the riders, but the riders will not fall. What they will feel is as if they are pinned to the wall, of course, due to centripetal acceleration. For the time 2.2 seconds, let's determine a rider's angular speed, omega, linear speed, v, angular acceleration, alpha, tangential acceleration, a, radial acceleration, ar, and total acceleration, the vector a. Okay? This is our game. Radius is 33.1 meters. At time equals 0, the game is just starting, so omega naught is 0. We don't know what acceleration is. We know at time t equals 2.3 seconds. We have no idea what the velocity is at that time. After that, the acceleration is 0. And our position is given by these things. We want omega, v, ar, at, and acceleration a. Let's do them one at a time. At t, 2.20 seconds, theta equals ct cubed. If I have theta, I can get omega. I differentiate it, 3ct squared. And if I have omega, I can find v by simply multiplying it by the radius. Then I want to find alpha. I differentiate again. I get 6ct. And then to find at, I simply multiply it by r. For ar, omega squared r. And my acceleration will be taking these two components together in quadrature. Any questions? Okay. Let's see if we have understood this properly. PIQ3. Let's see. The Earth rotates once per day about its axis, which is perpendicular to the plane of the equator and passes through the north geographic pole. So this is my axis of rotation. Where on the Earth's surface should you stand in order to have the smallest possible tangential speed? At the equator, at the geographic North Pole, at 45 degrees above the equator, or every point on Earth's surface has the same tangential speed, so, quit tripping. Okay. Let's see. Most people, 54 people, chose at the geographic North Pole, and 12 people chose every point on Earth's surface has the same tangential speed. Every point on Earth's surface has the same rotational velocity, not tangential speed. Tangential speed, V equals R omega. So if I look at it from above, if I have three people, one on the equator, one at 45 degrees, one at the very top, and I look at the Earth rotating, which one of them is rotating fastest and which one is smallest? Now this photo makes me always dizzy. V equals R omega. Where, if omega is the same everywhere, where is the smallest R? At the North Pole. So the correct answer is at the geographic North Pole. Okay, we'll do one more, and then we'll call this a day. Is it possible to build a clock in which the tips of the hour hand and the second hand move with the same tangential speed? So with V being the same. This is normally never done though. Why? Wait, there's a problem here. This should not say is it. It should say it is. So it is possible to build a clock in which the tips of the hour hand and the second hand move with the same tangential speed. But this is normally never done. Why? Okay. Most people said the length of the hour hand would be 720 times greater than the length of the second hand. And that is indeed correct. Now, remember, the hour hand moves one full rotation in an hour, in 60 minutes, in 3,600 seconds. So omega for hour will be 3,600, will be 2 pi over 3,600 seconds. But the second hand moves a full circle every 60 seconds. So omega second would be 2 pi over simply 60 seconds. Yeah. Now, if we want them to have the same tangential speed, V equals R omega, we would require R 2 pi over 3,600 to be equal to R 2 pi over 60. Now the 2 pi's will go away. R hour, R second. But you will end up with R hour over R second, 3,600 divided by 60. 360 divided by 6 is 720. So indeed, this is the reason why. Okay, that is all for today. We can call this the end of today. And we can continue next lecture, inshallah, with section 10.4.